I take my great opportunity and proud privilege to introduce him before all of you. Dr. Dahuri is currently working as a professor in the Department of Information and Communication Technology, Fakir Mohan University, Baleshwar, Odisha, since 2013. He has received his master's and PhD degrees in computer science from Utkal University, Bani Vihar, Odisha in 2001 and 2006 respectively. In 2010, he received Young Scientist Award in Engineering and Technology for the year 2008 from Odisha Vigyan Academy, Department of Science and Technology, Government of Odisha. In 2021, he has received Teacher Associateship for Research Excellence Fellowship from the Science and Engineering Research Board, that is SCRB, of Department of Science and Technology, Government of India, for 3 years to carry out intensive research on higher order neural networks for big data analysis, jointly at Indian Statistical Institute, Kolkata, and Fakir Mohan University, Baleshwar. His research interests include evolutionary computation, neural networks, pattern recognition, data warehousing and mining, object-oriented programming and its applications, and finally bioinformatics. He has already published about 200 research papers in reputed journals and conferences. He has published 5 textbooks for undergraduate and postgraduate students and edited more than 10 books of contemporary relevance. He has completed 3 different research projects obtained from DST, UGC, and DRDO. His H index as per Google Scholar is more than 25. As a part of academic collaboration, he has visited Ireland, New Zealand, Hong Kong, France, and Nepal. Sir, on behalf of Siksha O Anusandhan University, I welcome you to this FTP. It would be a matter of immense pleasure for all of us to hear from you. I now request you deliver your session. Over to you, Sachidanand, sir.
Yeah, thank you, Professor, for giving me a chance. Am I audible?
Yes, sir, you're audible.
Yeah. So thank you for giving me a chance to share my expertise in this great platform developed by Professor Mohanty and the team. I mean, Department of Electronics and Communication Engineering, SUA University.
Hello. Dr. Tehuri, your voice is not audible. Hello. Dr. Tehuri? I think he's having some technical issues.
Extremely sorry due to this network disturbance. So now I'm reaching to you all.
Yes, sir. You're audible,
Okay.
sir.
Sorry for the network disturbances. I do not know what is happening at my end. Anyway, so in this platform, I am going to discuss one of the core as well as important topics of artificial intelligence. No, I cannot say advances in artificial intelligence, but artificial intelligence. I hope this topic will definitely encourage you to work in this field. although this topic is not directly connected but indirectly connected to the field of artificial intelligence, you know, so I'm assuming you all know a little bit about artificial intelligence. um, and its allied field like you know, machine learning as well as deep learning. If you can visualize, if you can visualize in terms of sets, then you can say the machine learning is a subset of artificial intelligence, and deep learning is a subset of your machine learning. So in other words, you can say artificial intelligence is a superset. So in this set, so I mean this superset is containing sets like machine learning as well as deep learning. So nowadays people are very much excited to work on deep learning as well as machine learning, and they are applying in different fields like data science, big data analysis, etc., and so on. But I am not going to discuss on machine learning as well as the bit and byte of machine learning as well as deep learning. So one of the core components of artificial intelligence I am going to highlight here before you. uh, um, you know that the goal of artificial intelligence, the goal of artificial intelligence uh, is to develop a kind of system. That system may be a software system or maybe a hardware system driven by software system that can act and think like a rational human being. So that is the objective of artificial intelligence. That means you are going to design or develop a system which can act and think humanly as well as rationally. So with this objective, many scientists of this academic community, I mean those who are working in the area of artificial intelligence and its allied area, they are developing, they are contributing a lot, and many advances are really happening over the years in the field of artificial intelligence. So it is really a very big field. It is difficult for me to discuss all these things, but at least let me highlight one of the topic that is called uncovering Pareto optimality or uncovering Pareto front from um, multiple objective scenario and its post analysis. So let me present my presentation. Through this presentation, I will try to convince you about the topic. Okay. So shall I assume my slides are reaching to you all, visible to you all?
Yes, it's visible.
Visible, no. Okay. So thank you. So the title of my topic is Uncovering Pareto Front in Multi-Objective Optimization and its Post-Analysis. So before trying to convince you about Pareto Front, let me discuss what exactly multi-objective optimization, and then how do you uncover the Pareto Front and how it becomes a challenge for us, for the researchers who are working in multi-objective optimization. How difficult this problem. Let me try to convince you. A couple of slides. Yeah. So I am getting noise.
Right now, I have to for the audit.
So if you want to interrupt me, please let me know. Okay. Otherwise, don't make noise. So the moment you are talking in the background, then you please mute and then. Okay. So with a motivation, with a single motivation, we will move forward to learn what is Pareto front and what is multi-objective optimization and how they are related to each other, and what is post analysis, why post analysis is important. See, my topic is touching the four important components of artificial intelligence. One of the important components of artificial intelligence is a kind of knowledge management or knowledge representation, and also searching. And another one is maybe a kind of learning and constant satisfaction problem. So all these, this topic is touching all the four components. So I hope you will get flavor out of my discussion. So it has become, so with a single motivation, and it is really contributed by Milan Jelny, a professor of management system at the University of New York City. So he said, it has become more and more difficult to see the world around us in a unidimensional way, and to use only a single criterion when judging what we see. With this motivation, let us learn this topic. So this topic is a very interesting topic. So before jumping to multi-objective optimization, we need to understand what is single objective optimization. So through these slides, now probably we may able to distinguish how single objective is different from multi-objective problem. So the moment we are talking about single objective optimization, then we are saying when an optimization problem involves only one objective function, the task of finding the optimal solution is called single objective optimization. For example, if I will ask you, find out a car for me with minimum cost. Okay, I'm going to buy a car. By keeping in my mind only one objective, that is cost. That is, I'm trying to minimize the cost itself. No other objectives I am trying to involve here. Okay, so I'm trying to buy a car with minimum cost. Only one objective. With one objective, by fixing one objective, I'm trying to fulfill my task. Then it is a kind of single objective optimization. And in the case of single objective, it is very interesting that in the case of single objective optimization, we are trying to find the global optimal solution. So global optimal solution, we are looking for global optimal solution. We are not looking for local optimal solution, even though there are many local optimal solutions are spread over the short space, but we are looking for the global optimal solution. But in the contrary, multi-objective optimization, when an optimization problem involves more than one objective functions, of course, those functions are very conflicting to each other. The task of finding one or more optimal solutions is known as multi-objective optimization. So in this case, the same example can be recasted like, find out a car for me with minimum cost and maximum comfort. That means you are trying to buy a car by considering two objectives. Now, you are trying to minimize the cost as well as trying to maximize the comfort. So how do you get a car with minimum cost and maximum comfort? So this is the challenge involved in multi-objective optimization. Okay, are you getting my points? I'm asking the participants. So if you have any query up to this slide, yeah, please ask me. Okay. So now, from this slide, we can easily visualize how difficult a single objective optimization problem and how difficult a multi-objective optimization. This is a kind of simple, through this simple visualization, we can easily get. You see, in the case of single objective, in the left-hand side, okay, in the case of single objective optimization, we are trying to find out the global optimal. Here, the very peak one, the leftmost figure, upper corner. So this one is we are looking here in the case of single objective optimization, we are looking for global optimal solution, even though so many local optimal solutions are present in and around the global optimal solution. So So people are also saying until and unless you have a good technique or good method, then probably you may not reach to the global optimal solution. You may trap in local optimal solution. So therefore, while developing the optimization techniques or methods, people should be very careful. Okay. Then about the second figure, that means it has two objectives: price as well as luxury, or you can say cost and comfort. Y-axis is corresponds to comfort and x-axis corresponds to cost. Okay. Then of course you are trying to minimize the cost and maximize the comfort. Then you are getting so in this scenario you are getting four solutions, like solution 1, solution A, solution B, solution 2. Out of, you tell me, out of these four solutions, which one is better if you are considering two objectives while buying your vehicle? Can I say one is better than A, or A is better than B, or B is better than 2, or 2 is better than B, or B is better than A, or A is better than 1 with respect to both the objectives? You can say, okay, the solution number 1 is comparatively better than A with respect to price, but not better than A with respect to luxury. Similarly, solution A is better than solution B or solution 2 with respect to price, but not better than with respect to luxury. Similarly, solution 2 is better than solution 1 with respect to luxury, but not better than with respect to price. So in this scenario, you cannot say one is better than A, or A is better than B, or B is better than 2, or vice versa. But here, at this point, I can say, yes, all solutions are equally good. The moment I am considering two objectives, or I am trying to optimize these two objectives simultaneously, then all the solutions plotted here are equally good. Okay. Then let me cite some of the examples of multi-objective optimization problem. Many other problems of the life situations involve multiple objectives. As an example, locating a flat for me. I'm trying to buy a flat. And the moment I'm trying to buy a flat, then I am of course considering the cost. I'm trying to minimize the cost. How do I get a flat with minimum cost? And so many facilities like closer to my workplace, and closer to hospital, and closer to railway station, bus stop, market, and of course the flat is containing 3 bedrooms and 2 balconies, etc., etc. The moment I'm trying to get a flat by considering all these objectives, probably I won't get a flat for me in my lifetime. Yes or no? Uh, 1 second, I am presenting. Okay.
Ganga.
Am I audible?
Yes, sir.
Am I audible? Yeah. Actually, lots of problems I'm getting anyway. So now the slides are visible. Not visible.
Yes, sir.
Slides are visible.
Yes, sir.
Okay.
Visible, sir.
Okay. Then. So. Now the thing is, suppose I am trying to buy a flat. Then if I am looking for, if I am trying to minimize the cost as well as to maximize the facilities, then probably I may not get a flat. Okay. So in this scenario, so how do you take the decision? How do you take the, so because you are getting more and more number of solutions and all solutions are equally good, you cannot say one solution is bad over other solutions. So therefore the challenge is how do you select a particular solution. Based on that you can take the final decision. Then another example of multi-objective optimization, that is redundancy allocation problems. That means here so this is a kind of engineering problem, and this problem is a kind of, we are trying to develop a system, and this system is containing so many subsystems. That means N1 subsystem N1, subsystem N2, and subsystem NS. I mean S subsystems, and within a particular subsystem there are many components. Like in the first subsystem we have N1 number of components, in the second subsystem you have N2 number of components, in the S and so on. In the S subsystem you have NS number of components. So here the objective is, so this problem is, can also be visualized as a multi-objective optimization problem, because hello.
Excuse me, sir. Slides are not visible, sir.
Okay, so that's why I'm asking. No,
Not
slides.
visible, sir.
Okay. Now it is visible.
No, sir. No.
Now
Yes,
it is
sir. Now it
visible?
is visible, sir. Yes,
Okay,
sir.
okay.
It is visible now.
Okay. So
Thank you, sir.
So, so this is a kind of engineering problem. So redundancy allocation problems. We have a system. We are trying to develop a system. In the system, we have the objectives like maximize the reliability of the system and minimize the cost, as well as minimize the weight of the system. So three objectives are involved here. I mean, your reliability as well as cost as well as weight. Okay, the system is like this. In this system, we have S subsystems, and in each subsystem we have so many components. Okay, in order to enhance the reliability of the system, then we need to add more and more number of components. The moment you are adding more and more number of components, though you are going to enhance the reliability, but at the same time weight and cost of the system will increase accordingly. Now the thing is, how do you optimize the three objectives like reliability of the system and minimize the, maximize the reliability of the system, minimize the number of minimize the cost as well as minimize the weight. So it is also a very big challenge in the community of systems engineering. And one more example. So in determining an electric route for power transmission in a kind of city like Bhubaneswar or Baleshwar, several objectives could be considered, like cost, health, reliability, importance of areas, etc. Similarly, we have so many examples. I'm not going to cite all the examples. Anyway, one more interesting example of multi-objective. So this is also a kind of multi-objective optimization problem. Some of the objectives here are more is good and less is good. So I'm not going to discuss all those things. Anyway, so let me go into the deep of this single objective optimization. I mean mathematical formula of single objective global minimization problem as well as multi-objective optimization problem. So from the mathematics point of view, we can visualize like given a function f whose domain is omega and it produces, of course, the range. It produces a real number in the range. So that omega is the feasible region. That is the feasible region not equal to phi. For x vector belongs to the feasible region, the value of f star equal to f of x vector star greater than minus infinity is called a global minimum. If and only if for all x vector belongs to the feasible region and f of x vector star definitely less than equal to f of x vector. So where x vector star is the global minimum solution and f is the objective function and omega is the feasible region. From the feasible region, you are picking up so many I mean in the decision space. In the decision space, you have so many decision variables, and those variables and maybe the solutions are there. Then you are picking up, and then you are mapping the objective space, and accordingly you are trying to get the global optimal solution or global minimal solution. So, for example, in this, in order to understand this definition, probably you can also solve a very small problem. This is known as 0-1 knapsack problem. This problem is, of course, a kind of intractable problem, and that is very famous and very popular in computer science. So 0-1 knapsack problem. So this problem is like this. You have a knapsack, I mean the knapsack problem with n items. So you have a knapsack, you are trying to pick up n items. And the size of the knapsack is b, and 3 sets of variables related to the items, decision variables, positive weights, and profits. And for each I will vary from 1 to n. Xi is either 0 or 1. The Wi and Pi represent the weight and profit of integers of the ith respectively. The single objective knapsack problem can be formulated like this. Okay. In a kind of English sentence, let me try to convince you. The knapsack problem is like this. You have a knapsack and there are many items available, and you are trying to put in your bag, in your knapsack, and your knapsack has certain capacity, and each item is associated with cost as well as weight as well as profit. Cost as well as weight. Okay? Each item is associated with weight as well as profit. So how do you pick the items in such a way that you can maximize the profit, and with a constant that the weight of the total weight of the items you have put in your bag should not be greater than b, size of the bag. So that is the problem. And another thing is, and the very important thing is, you are not going to take the fraction of the or part of the item. You have to take the full item you need to take, whole. You cannot take part of the item. Either the item is included or not included. So, so that item here in this case is denoted as like x1, x2, and xn, and x1 is associated with weight as well as profit. So maximize P equal to summation I varies from 1 to n Pi xi, subject to the constant that I varies from 1 to n Wi xi less than equal to B. So xi, either you are going to take the whole item or you are going to leave the item. So you are not going to take the part of the items. Okay. So that is your single objective optimization problem. And in the case of multi-objective optimization problem, you are going to optimize a vector of function. You are going to optimize a vector of function, of course, with certain constraints, and the constraints may be equal, so equate to 0, or maybe greater than or less than equal to 0. Okay. With this, let me highlight one of the problems I've plotted here, that multi-objective of that. Okay, so now the thing is, you can also, the very interesting thing is, so we have visualized here 0-1 knapsack problem as a single objective optimization problem. So you can also recast this problem to a multi-objective optimization problem. So what are the objectives? The moment you are going to recast to multi-objective optimization problem, then you have to have here the vector of function. What are those functions you are considering? You are going to have the function like maximization of profit, as well as you are removing the constraints, and the constant becomes another objective. Okay, so you have two objectives. I mean, maximize P and minimize W. Weight, you need to minimize the weight as well as maximize profit. So your 0-1 knapsack problem, even though you had visualized it as a kind of single objective optimization problem, now it is recasted to multi-objective optimization problem. So these two objectives are conflicting in nature. So I'm plotting, this is a minimization of weights. The x-axis corresponds to weights and y-axis corresponds to profits. Then we have a set of solutions. You see the set of solutions, and all the solutions are not important for us or not acceptable. Few solutions are really required, and rest of the solutions may be simply discarded from the canvas. Okay. Sorry. So the solutions from this situation, the solutions which you are going to accept are known as non-dominated solutions, and the solutions which are dominated by these solutions, I mean highlighted solutions, are known as they are not required. They are dominated solutions. Dominated solutions are simply discarded from this scenario, and non-dominated, we are going to keep only the non-dominated solutions. Finally, the non-dominated solutions are going to develop the Pareto front. And the non-dominated people are also saying non-dominated solutions are Pareto solutions. Okay, so we will get all those concepts like what is Pareto solution, what is non-dominated solutions, what is dominated solutions in the next couple of slides. Then let me just highlight types of multi-objective optimization problem. The moment we are considering the multi-objective optimization problems, then either you are going to minimize all the objectives, or you are going to maximize all the objectives, or you are going to minimize some objectives as well as maximize rest of the objectives. Then why evolutionary algorithm for multi-objective problem? So this is really very interesting. Why people are excited to use evolutionary algorithms? I mean, genetic algorithms, or genetic programming, or evolutionary strategies, or maybe swarm optimization techniques. Nowadays, people are also applying, for example, PSO, particle swarm optimization, and also like ant colony optimization, and also non-evolutionary algorithms like, for example, population or stochastic based search algorithm like simulated tunneling. Why people are excited to apply in multi-objective optimization problem? Yeah, the simple motivation behind this, like the complexity of the problem, because 0-1 knapsack problem is a solution by conventional technique. Probably you may not get the if you are looking for exact solution, probably you may not get the solution in time. You need to wait for long. So another thing is complexity includes large. You can say what do you mean by complexities? So the complexity includes large search space, and of course, it also includes noise, and you won't get a continuous Pareto front. You may obtain a Pareto front which is very much discontinuous, and you know that it is very difficult to optimize a discrete function if the search space itself contain discrete Pareto front. Really a very top job by getting or by uncovering the Pareto front through conventional approaches. So therefore, people are looking for evolutionary algorithms or maybe the swarm algorithms, etc. And also it is interesting that the evolutionary algorithms are population based. They can tackle the large search space as well as distant Pareto clubs very effectively. And it has already been proved through the through theoretical, proved by theorems or maybe from application. People have established this by applying widely in different fields and also theoretically also proved. So objectives in multi-objective optimization problem. So what are the objectives? The objectives are like to find a set of solutions as close as possible to the Pareto front. So this is a big challenge. This is a big challenge standing before us, to find a set of solutions as close as possible to the Pareto optimal. Even though, of course, we are looking for uncovering true Pareto front, but it is really very difficult for us. But at least we can obtain set of solutions, and they are very close. Non-dominated solutions very close to the optimal Pareto front. Then to find a set of solutions as diverse as possible. So as MOES deals with, multi-objective evolutionary algorithms deals with two spaces, decision variable space as well as objective space. Diversity can be easily defined in both these spaces. Diversity in one space usually means diversity in other space. This may not be also in all problems. The task is to find set of solutions having a good diversity in the desired space. So this is a simple mapping, so you can understand. So this figure is extracted from my contribution, one of my contributions. So this is a kind of mapping between decision variable and so this is the right hand side is the objective space and the left hand side is the decision space. The moment you are trying to maintaining diversity in the decision space, of course you are maintaining the diversity in objective space. So the objective space, from the objective space you are trying to obtain the non-dominated solutions, and you are discarding the dominated solutions. Then now let us understand what is domination or what is dominated solution. So this is a very clear definition, and this definition I have taken from the book written by Kalyanamay Dev. So of course this definition is very true. This is very true in the field of very true as well as acceptable in the field of multi-objective optimization. A solution X1 dominate other solution X2 if both conditions 1 and 2 are. The solution X1 is no worse than X2, and the solution X1 is strictly better than X2. So these two conditions, if these two conditions are satisfied, then we can say X1 dominate X2, or X2 is dominated by X1. When X2 is dominated by X1, if X1 is no worse than X2, and x1 is strictly better than x2. These two conditions should be satisfied. Then only you can say you can be in a position to find out the dominated solution out of many solutions. Okay. So here the task is to find out the dominated solutions. The core of this algorithm or approach is to find the set of dominated solutions. I mean non-dominated solutions, and you are trying to discard the dominated solutions. And the moment you are looking for non-dominated solution, you are searching for non-dominated solution from the search space. Then after getting all the non-dominated solutions, then you are getting a Pareto front. So that is my intention, how to uncover a Pareto front from the search space. So this is a simple visualization. You can easily understand what is dominated solution, what is non-dominated solution. You see the x-axis. Am I audible?
Sir, you are audible, but your slide is not shared.
Slide is not shared?
Slide
Yes,
is
sir.
visible, sir. Slide is
Slide is
visible.
visible.
Probably your network.
Yes, sir, it is visible only.
You check your network, please.
Okay, sir.
Okay. Otherwise, I will after my lecture I will share you. I will share with you my slides. Okay, all my
Thank you.
slides.
Thanks a lot, sir. Please sharing your slides.
Yeah. Okay. So from this simple visualization, you can understand. So what is a dominated solution? What is a non-dominated solution? So the x-axis corresponds to maximization function, and the y-axis corresponds to minimization function. I mean maximize f1 as well as minimize f2. The moment we are trying to maximize f1 and minimize f2, then we have a set of solutions like 1, 2, 3, 4, 5, 6. Out of these 6 solutions, which are the non-dominated solutions and which are the non-dominated solutions? That we need to identify here by using the definition we got in the previous slide. Okay. So let me tell you. So okay, now okay, I am not going to tell you which are the dominated solutions and which are the non-dominated solutions. Now it is your turn to find out which are the dominated solution and which are the non-dominated solutions. Since you have got the definition of domination or non-dominated solution or dominated solution, can you please identify? So okay, let me interact with you through these slides. Okay, let us compare solution 1 and 2. So if we are comparing 1 and 2, which one will be better? If we are going to compare 1 and 2, which one will be better? 2 is better, no? Because in all objectives, 2 is better than 1. Yes or no?
Yes, sir. 2 is better than 1.
Yes, because with respect to f1, 2 is better than 1. Similarly, with respect to f2, 2 is also better than 1. Okay. So therefore, 1 is dominated by 2. Who is dominating 1? So 2 is dominating 1. So 1 is discarded from this pool. Okay. In this way, you need to find out all the non-dominated solutions. According to the definitions, solution 1, solution 2, similarly 4 is better than 2 in all objectives. With respect to all objectives, 4 is better than 2. Therefore, 2 is dominated by 4. But 2 is not dominated by okay, 2 is not dominated by 3. 2 is not dominated by 3, but 2 is dominated by 4. So 1 and 2 is discarded. If you say here, if a solution is dominated by at least one of the solutions from this pool, then that is declared as dominated solution, and simply you need to discard. Okay, so that you can reduce the time complexity. So we have also in the year of maybe 2010, we have a paper like how to find out the non-dominated solution by divide and conquer approach. So we have reduced the time complexity a lot. So if you want to read that paper, then please refer IEEE site. So you will get that. In a conference we have published that one. That is available in the web space, so you can search. Okay. Then similarly, 3 and 4, of course, by 6, the 4 as well as 3 is dominated. So finally, we have the solutions 6 and 5. So these two solutions are non-dominated. Okay? You cannot say 6 is better than 5 with respect to F1 and F2, or 5 is better than with respect to F1 and F2. So therefore, 5 and 6 are the non-dominated solution. And in this scenario, they are constituting the Pareto front. So here the Pareto front is containing two solutions. Okay. Then properties of dominance. So we have a properties like reflexive, symmetric, transitive. So reflexive, the dominance relation is not reflexive, and of course symmetric, the dominance relation is also not symmetric, and transitive, the dominance relation is transitive. In order for a binary relation to qualify as an ordering relation, it must be at least transitive. Thus, dominance relation is only a strict partial order relation. Then Pareto optimality. So non-dominated set, global Pareto optimal set, and we have locally Pareto optimal set. So we got the concept of non-dominated set, as well as we know that if it is a global Pareto optimal set, then we are considering the entire feasible search space or region. And the moment we are looking for locally Pareto optimal set, then we are just making constraint to a certain feasible region of the search space. Then that is local Pareto optimal set. Also, in the multi-objective optimization theory, a concept is also very popular, that is strong dominance and weakly non-dominated solution. Okay. So a solution X1 strongly dominates a solution X2 if solution X1 is strictly better than solution X2 in all objectives. If the solution, if a particular solution is strictly better than another solution with respect to all the objectives, then that is a kind of strongly dominant solution or strong dominant solution. Okay. Weakly non-dominated set among a set of solutions P, the weakly non-dominated set of solutions P prime are those that are not strongly dominated by any other member of this set. So Pareto front, finally we are getting a Pareto front, and this is containing all the non-dominated solutions. So you just see this visualization. So in the bottom we have a set of solutions. You see this visualization containing many Pareto fronts, but the bottom line is the real Pareto, I mean true Pareto front. So we are looking for this true Pareto front. So somebody can get a Pareto front above this line and then above that line like this, but we are looking for true Pareto front. So this is a very simple example given here. Then you can just try. You can implement this. So this is a very simple function. F1x is given x1 and f2x equal to 1 plus x2 divided by x1. So the variables are also x1 and x2 are restricted. I mean they have the constant, like x1 is lies between 0.1 to 1 and x2 is lies between 0 and 5. So similarly we have one more example, f1x. So x1 and f2x 1 plus x2 minus x1 square. So so x1 has the boundary between 0 and 1, and x2 has also the boundary like left boundary as well as right boundary. So 0 and 3. So you can also explore this from this search space. You see, so lots of Pareto front. We need to identify the true Pareto. Then what are the multi-objective optimization approaches? What are the approaches? So there are many approaches, like very few popular approaches like weighted sum approaches, lexicography approaches, Pareto approaches. So weighted sum approach is like even though you have different objectives, then what you will do, you just log those objectives. by associating weight parameter, with each of the objectives. Then that means you are just mapping multi-objective problem to a single objective one, and then you can apply your conventional technique. So no need to explicitly design multi-objective algorithm for this. Even though you have multiple objectives for your problem, but you are recasting to single objective optimization problem by making a summation, and each function is associated with weight variable. There are certain disadvantages associated with this method. First one is maybe you won't get a set of Pareto optimal solution. You won't get a set of non-dominated solution. Hopefully, you will get it. Now audible?
Yes, sir.
Visible also?
Audible, sir.
Yes, sir.
Visible
Visible
also,
also.
sir.
Okay.
Yes.
So
Sir,
How
sometimes
to assign these weights, sir?
yeah. So
How to assign these weights?
okay. Few people are following random approach. They are randomly assigning weight between 0 and 1. So this is one obvious approach. You just create random numbers uniformly and then associate. I mean, then you assign to each objective. So that is obvious approach. And few people are assigning weights based on the empirical analysis. Based on the strong domain as well as empirical analysis, they are assigning weight values.
Can you discuss little bit a last part?
Which one? Which one, please?
This empirical analysis.
That empirical analysis means, for example, you are optimizing a function. Okay, optimizing a function, set of functions, and you know that the constraint of each and individual functions, and also you know the domain restriction of the functions. Then from this you can say, you can from the domain as well as from your mathematical analysis, you can say, okay, if the weight value, if I'm going to assign the weight value between 0.2 to 0.3 for this objective, then it will be better. Otherwise, it may be a kind of unbiased. I mean, sorry, it may be a kind of biased thing. Okay. So those things happen.
So, sir, in that case, we need a strong domain expertise.
Yeah, I cannot say strong, but you have to have little domain knowledge as well as you have to have some experience about the task for which you are looking for the solution.
Okay. Thank you, sir.
Yeah. A little domain knowledge is always required. Otherwise, it is a really tough job to solve the problem. Okay, so each and every problem, the moment you are going to solve a problem, at least try to acquire the domain knowledge. Otherwise, it is a kind of you are solving the problem through a blind approach. Then the next approach is lexicography approach. In this lexicography approach, different priorities are assigned to different objectives, and then the objectives are optimized in order of their priority. So here in the lexicography approach, you are setting priorities. Then let me review some of the classical methods. Like we have discussed two methods, like weighted sum approaches. I mean, methods coming under weighted sum approach, and methods coming under lexicography approach. So, in a nutshell, we can say only one Pareto optimal solution can be expected to found in one simulation run of a classical algorithm. Not all Pareto optimal solution can be found by some algorithms in non-convex multi-objective optimization problems. All algorithms require some problem knowledge, such as suitable weights, epsilon, or target values, etc. So some problem knowledge requires. Otherwise, you may land with a solution. That solution may not be potentially useful. I can say potentially useful. Okay. So the last approach, that is known as Pareto approaches. So the Pareto approaches are really very interesting, and in order to simultaneously uncovering all the non-dominated solution for a Pareto front, we are applying like multi-objective genetic algorithms, multi-objective Pareto particle swarm optimization, multi-objective artificial bee colony algorithm, and also people are applying ant colony optimization, multi-objective ant colony optimization. Recently, also people are tried to get solution through multi-objective biogeography based optimization. So many algorithms have been developed over the years for getting the Pareto front or uncovering the Pareto front. But I cannot say whether you are going to get the true Pareto front or not. Okay. So okay. So one of the algorithms, multi-objective genetic algorithms, let me quickly highlight this. So because under this multi-objective genetic algorithm, so many algorithms are there, but at least I need to convince you with a single very element, the algorithm which was developed by Sapir, and that is known as the the first algorithm introduced in the field of multi-objective optimization from evolutionary algorithm angle. Okay, so in order to understand multi-objective genetic algorithms, you need to have to have sound knowledge on genetic algorithms. So, do you have idea about genetic algorithms? I hope you have little idea about genetic algorithms. So, so genetic algorithm, quickly let us cover this. So genetic algorithm, so it is an evolutionary algorithm, and also it is people are also saying population-based stochastic algorithms. So it has steps like initialization of population, fitness assignment, selection, crossover, mutation, and it is checking whether the performance is satisfactory or not. If the performance is satisfactory, then okay, declare the result. Otherwise, you iterate this for a couple of iterations or until the stopping criterion is satisfied. So this is a quick scan of genetic algorithm, about genetic algorithms. Then the first algorithm developed in this community, that is vector evaluated genetic algorithm, that is known as Vega. So this Vega algorithm has been introduced by Sapir to find the non-dominated solutions. Here what happens, so initialize the population and you divide the population into case of populations and evaluate the fitness, and then apply the selection operator, and then combine all the population, and then shuffle entire population and make crossover mutation, and then test whether the performance is satisfactory or not. If it is satisfied, then stop, otherwise you just iterate this. So this is the first evolutionary algorithms, evolutionary algorithm for multi-objective optimization problems. A few more popular algorithms like vector optimized evolutionary strategies, multi-objective genetic algorithm, non-dominated sorting genetic algorithm, is a NPGA, predator-prey evolution strategy, distributed sharing GA. So many over the years, so many algorithms, and NSGA2 until 2000, NSGA2 was very popular. So that is obviously contributed by Kalyan Moitev. And it has lots of applications, like people are also applying in data mining, real-time task scheduling, and groundwater contamination, land use management, intrusion detection, combinatorial problem like flow scheduling, vehicle routing problem, zero-one knapsack problem, etc. etc. So multi-objective optimization problem has been widely used and also applied. More about multi-objective optimization problem and approaches. If you want more about this, then please refer Professor Carlos S. Ciolo site. He is one of the best scientists in the field of multi-objective optimization problem. So I suggest, if you want more about the multi-objective optimization problem, please visit this site. This site is from this site you will get lots of contributions which are really made for to learn multi-objective optimization and contributed by Professor Carlos. And some of the references you can also use for your research, like we have also certain contributions, and these contributions are really interesting, like surrogate assisted multi-objective genetic algorithms for a fuzzy rule based system. We have developed few. So if you are interested, then you please go through these references. Then I don't think I have sufficient time, so I have a meeting now, so I am leaving. But prior to that, it is difficult for me for discussing the post analysis. Maybe I will share this slide so that we can learn easily, because the post analysis is very simple. So actually, I was trying to discuss two approaches for post analysis of Pareto front, like weighted score method as well as Topsis method. The weighted score approach is very simple. Just you assign the weight and then find out the utility, and then try to obtain the multiply the weight values and obtain the score. And from the score, then you can get, okay, then you can get the best score you can get, and accordingly you can choose the option. So this is the civic is the option in this case, because it is giving more score. So with respect to three objectives: style and reliability and fuel cost. Similarly, you can apply the Topsis method. So this is also a very popular and simple method, easy to understand method, technique of order preference by similarity to ideal solution. So you can also use this method to get the options. Out of many options, you can get the option very easily, and you can you have much more flexibility to decide which option you want to consider. So with this, I am concluding. If you want to ask few questions, please ask. And so in the last slide, with a business, I'm just cross-selling. So these are my books. You can also refer. So big thanks for patiently listening me. So if you have questions, then you please ask me. Professor Mohanty, I have completed. So actually, I have right now I have a meeting. I need to switch to another meeting. If you so if the participants are planning or interested to ask me a few questions, then I will be very happy. And
okay, any question from audience? Hello, is it audible?
Yes, sir.
Any question from audience?
Sir, am I audible?
Yes, audible, please.
Sir, regarding the genetic algorithm approaches that you have discussed, what is the best and optimized way to select the algorithm?
No, 1 second, please. What is the?
Sir, what will be the optimized way to select which type of genetic algorithm we should choose?
Oh, that means out of several genetic algorithms, according to the complexity of the problem, you need to course, based on the complexity of the problem, there are several genetic algorithms over the year developed. Like for example, few genetic algorithms developed, like compact genetic algorithm and probabilistic genetic algorithms, and it is based on the complexity of the problem. Okay.
Okay, sir.
So I cannot say this. I mean, canonical genetic algorithm is better than compact genetic algorithm. I cannot say, because until and unless you you thoroughly studied the problem, yeah, it is very difficult.
Sir, like there are many parameters depending upon algorithm. Like there is fitness score. There is
Yeah,
parameter
yeah,
known as
I
the
understand. I understand. In that case, you can go for canonical genetic algorithm. That is the best approach. And also the
Okay.
binary representation. Your chromosome should be binary, and you need to accordingly choose the mutation and crossover operators. And also you
Okay,
need
sir.
to accordingly choose the selection operators, because there are so many
So
selection.
depending upon the parameters and the data that we are putting upon, we need to
Yeah.
decide the algorithm based on the complexity and accuracy.
Yeah, another thing is, more vital thing is, suppose you are trying to optimize many parameters, okay, and those
Mhm.
parameters are real numbers, okay. Then the moment
Yes.
you are dealing with binary chromosome, then probably you may face difficulty. In that case, you can represent real number as a chromosome, and accordingly your mutation and crossover operator will be changed. Okay.
Oh, okay, sir.
So real time, I mean, one genetic algorithm that is available, that is called real coded genetic algorithm. Okay, that also you can apply.
Okay, sir. Thank you,
And
sir.
people are also hybridizing. I mean, few parameters are real number and few are just integer. So they are just combinedly they are I mean, using, like for example, integers, they are going for binary representation, and for real numbers they are going for real coded. Okay, that is also
Okay, sir.
possible. Many flexibilities are there. You can do.
Okay, okay, sir.
So thank you.
Okay, thank you very
Thank you,
much
Yeah,
for
yeah.
the informative talk, Professor
Yeah,
Sakshi.
actually, I want to ask you, what is your name, please?